believe I can solve
I've never drank coffee.
Well, we didn't do it.
Probability set 3, we're going to start with problem 10. I think it's so bad. What group actually did that?
That was awesome. Quick question, Jhevon.
Yep.
Will we be having class next Tuesday morning?
Yes. Yes! Okay. A casino has a game with $1 buy-in. Okay, so you pay $1 to play this game. In this game, you would toss a dice, and you lose or earn money based on the following. If the die lands on 6, you get $3. If it lands on 3, you get nothing. If it lands on 1 or 2 or 5, you would lose $1. If it lands on a 4, you would gain $1. XP, the expected earnings. Find a probability distribution for X, which means you need to tell me what are all the possible values that X can take on, and what is the probability that it takes on such values. Go.
So for the X part,
Yeah.
we did the money you win.
Yeah.
So we did like $3, $0, -1 and 1 for X.
3, 0, -1, and 1.
And then under that we did the probability of them, and for 3 it was 1/6, because it's just 6.
I probably wouldn't have chosen those numbers.
Did you like do the -1?
Yeah, there's a -1 in front. So when you walk into this casino, you lose $1 just by sitting at the tables. So technically, I probably want to decrease all of these by 1. So technically, you play this game, you win $3, you really only earn 2. Because one of those dollars you got, it was kind of your $1 that they gave you back.
So you're not doing that.
Huh? So we're doing net earnings, yeah. So
Is it okay if we subtracted the 1 at the end?
Yeah, I did the math both ways, you have the same number.
well, yes. Did you guys subtract it? at the end?
Yeah, we
Yeah,
just
we
subtracted
just
it.
didn't do it in the.
You subtracted out.
So we just used those values that they gave us and did it.
Okay. What was the probability that you would win $3?
1/6.
Right, you win 3 if it lands on a 6. There's a 1/6 chance. It's just a fair die. You get nothing probability.
1/6.
Also 1/6. That's if it lands on a 3. What about -1? You lose 1.
1/2.
1/2, because there are 3 out of 6 ways that you could get that possibility. And then
1/6.
1/6 if it lands on a 4. I also want you to appreciate something. What is the sum of these guys over here?
1.
1, right? Which should add up to 1, right? Because that's all possibilities, right? And I just found the probability of all possibilities. By our axiom, it must add up to 1. So it's also the case that once you have a probability distribution, the sum of all probabilities must add up to 1. If they don't, you did something incorrect somewhere. It's also the case that if you didn't know one of these situations, you could actually figure it out by just taking 1 and subtracting all the others. So that's worth mentioning. So that would be the probability distribution. And so, how much money do you expect to win on average? So this was A. Just do the probability distribution. B. How do you calculate how much you expect to win?
We multiplied each X by the probability of X.
Right, so you calculated the expected earnings, which is just the expected value of X. And that's going to be 3 times 1 over 6 plus 0 times 1 over 6 plus -1 times 1/2 plus 1 times 1/6.
And then we subtracted 1 at the end, because we didn't like factor in the 1.
The buy-in.
Yeah, the buy-in.
So you subtracted 1. That checks out.
And it's negative 83 cents.
Minus Yeah, sometimes people forget to actually do that. So I normally just do it right up front. So I would have written the tables. So this is the subtract the buy-in. Although I would just mention here, probably do it up front. So I would have put this as, say, 2 and -1 and -2 and 0. And then you should get -83 cents without you having to remember to subtract this thing. So technically here what you did was the expected value minus the buy-in. And that's going to be equal to this. So is the game worth playing?
No.
No, you lose 83 cents on the dollar. What does it even mean to lose 83 cents? That's not even one of the monetary values that we could have. What does it mean you lose 83 cents? Well, yeah.
If you were to play like a lot of times,
Right,
you would
exactly.
actually approach that.
So this is going back to one of the ideas that we said from the last time. This is on the aggregate. If you were to play many times, right? You lose 83 cents on the dollar. So, that's just a small game, very small monetary prizes. Problem 11 makes it a little bit more interesting. Problem 11. It's not exactly, but it's more akin to like the lotto. You have a very large sum of money that you can win. So in problem 11, there's a $5 buy-in. Okay? So you pay $5 to play this game. You will select 3 cards at random without replacement from a standard deck. If you select the ace of clubs, the 10 of clubs, and the 7 of clubs in any order, it doesn't matter, you win $10,000. You pay $5 and you can win $10,000. Of course, there's going to be a big sign on that game, win $10,000. If you select 3 kings, you win $1,000. Okay, so you get 3 kings, I'll give you $1,000. All you have to do is give me 5. Otherwise, you'll lose $10, right? So you pay $5, and if you don't get one of these 2 things, you have to pay me an additional $10. Okay, so X is the amount of money that you end up walking away with. What are the possibilities here? I don't know which group did this one. Which group this one?
Oh, that's what we don't have any notes on it left. So I'm kind of.
So just hand it in.
Yeah, you know, we have it.
Okay, so didn't take a picture, didn't take anything? Okay.
No, what did you ask? Question. What? No. Like.
Oh, problem 11.
Yeah, no. What do you ask? Like.
Yeah, like specifically how you set
I
up
don't know.
I don't know. Okay. So, I guess we're gonna have to do this one. So, what are the possible earnings you can have here?
$10,000.
Well, 10,000 minus the $5
I'm not gonna
buy.
try.
So, 999.
Wait, can we subtract that?
You can just do it at the end.
Yeah. Can we do it at the end again?
Yeah, I could.
I like it.
This
This is worth a lot of money.
It's worth a lot of money, right? What about you could win $1,000? So that's 995. Or the last case, the case that no one's gonna think about. Come on, $10,000. That's what you're gonna focus on. You could lose 15. Okay, let's do these one at a time. What's the chances that you'll win that?
Why would you lose 15 if you only, the buy-in's $5 for 3 cards?
Because you lose an additional 10. There's a situation where you would lose 10 if you don't get one of these two things. Okay, what's the probability that I'll actually get the 10,000?
I'm not gonna try.
1-0.
We're gonna figure out what this goes there.
Can I try?
Yeah? Try to remember what you guys did. What is it?
Is it? I did 1/52 times 1/51 times 1/50. So that was 0.0000075.
Agreed?
Yeah.
Why? Explain. Why the 1/52? Yeah.
Would it be 4/52? And 3/51? And 2/52?
But it's only,
There are
I thought
three
we were
cards.
doing the king's one, my bad.
Yeah, we're doing the 10,000. So the ace of clubs, the 10 of clubs, and the 7 of clubs. Yeah.
Those are like unique cards. There's only one of them in the deck, so it's and you don't replace it. So it's just probably choosing that one card out of the remaining deck. All
Okay, so this one is representing what?
It's in any
order.
order.
One of the 3 games.
That one can represent one of the 3. Yeah.
Are those actually like conditional probabilities that you send in your tree diagram?
These are, but why the 1?
Oh.
It's only one 10 of clubs.
Yeah, wouldn't it be 4/51?
No, because it's the.
There's only one ace of clubs.
Yeah,
There's only one ace of clubs. There's only one 7 of clubs.
Yeah.
Oh, so there's one ace of clubs, one 10 of clubs, one 7 of clubs.
Yeah, that's what I was trying to say.
What if I didn't pick the ace of clubs first?
Oh, so there's multiple ways.
In any order.
There's multiple ways that you can do this, right? There's no any order.
Alright, what if we handed in?
A better thing. 3, 2, 1 would be what? You can pick any of the 3 cards out of 52. Once you've chosen one of those 3 cards, there are now only 2 of those 3 cards left. Once you've chosen that one, there's now only 1 card left. So this would account for any order. Basically, the 1/52, this, that would have happened multiple times. It would have happened in essentially 3 choose 2 ways, right? So that's one way to actually come up with it. Another way is to say, well, I just want the size of A over the size of S way. What are all the possible 3-card hands you can take? How many of them are there? Well, order doesn't matter, so it's 52, choose 3. And I want one specific combination of 3 cards. Does it give me this? So there's only one combination of 3 cards out of 52 choose 3 cards that I could have. That will give me that 10,000. You'll notice that this is also the same thing because 52 choose 3 is actually 52 times 51 times 50 over 3 times 2 times 1. And if you keep change flip, you get the 3 times 2 times 1 over the 52, 51, 50. So you have to be careful. Order does not matter. They didn't say you have to pick this one first and then that one second and then this one third, right? So you have to, because to account for the order, you decrease the sample size and as well the numerator will change at the same time. Or without order, you might think combinations, and this would have been the way to do it with combinations. In either case, we would end up with, what would we end up with?
1/22,000.
22?
22-1.
Like that?
Yep.
Okay, what about, what about winning the 1,000?
So 4 choose 3 over 52 choose 3. If I'm not mistaken.
Right, and it would also be like you could do the 4 times 3 times 2.
Right.
Or something like that. So something here, you could do like the out of 4 kings, choose 3 of them, and out of that. That would end up being what?
1 over 5525 rather.
5.5?
5.
Huh?
5525.
5.525.
Yes.
Okay. And what's this guy? Everything else, which is just going to be 1 minus those two. So if I take 1 minus this minus that, write as a fraction, what is that? So this one is 1 minus other two columns. What is that?
It's going to be 22,095 over 22,100.
So that's what our probability distribution is going to look like. Would you want to play this game?
No.
No. Don't put on
You
the
could win $10,000 though.
Depends on. Alright, maybe I'll play. Depends on what you want.
I play. I mean, you're in Vegas. It's $5. Come on, for the experience. I play, but I wouldn't seriously think I'm gonna win. You know what I mean? Like, there's a difference. When you have a problem, is when you like. Man, I think I feel this is definitely gonna be it. You know, this is the mortgage payment right here. Like when you go in like that, then dude, you got a problem. If you're just lose $5, just have a little fun. I wouldn't seriously play this game because if you look at the expected value.
I feel like I'm in probably Vegas that $15.
Yeah, if you were to play this game over and over. Okay, do it again. Another $5. Another $5. I feel like I'm getting lucky, man. Another 5. I'm gonna win that 10,000. Another 5. You keep doing it over and over again. That's how. In the long run, what are you gonna expect to happen? Well, there's a chance you can win that 9,995. Probability is gonna be that. There's also a chance you could win $1,000, which ain't too shabby, not too bad. Probability is that. But there's a chance that you could lose $15, and the chances of that is nearly 1, right? It's like literally 22,095 over 22,100. What is this roughly?
So what was your choice of game in Vegas?
It's not in the part of the question. What is this?
No, seriously.
Watch like 20 months. Oh man.
Well, you have to learn.
True, you gotta learn how to count cards.
What is it? Focus, this. What is this?
Is it black?
Negative.
That's why.
Negative what?
14.36. Yeah.
14.
It's easy. Probably easiest for this one.
Crabs. It's crabs.
So on average, you're $14 in the hole. That's worse than the last game.
Isn't that interesting? That's the first thing that teaches me.
So I mean, yes, it's very enticing, and this actually shows you how something as crazy as like a casino could even be a business that someone would even like. Why would you even make that a business? Okay, I'm just gonna allow this person to walk into my establishment, roll a pair of dice, and just take my money. Like, why would you do that? Well, no, but you have to make money at the end of the day, right? So the thing is, they set up a game that entices you. It's like, I could win 10,000, and they lure you in. Okay, come play my game, right? And it's possible that you're going to actually win $10,000, but in the long run, if they get hundreds of people to play that game, thousands of people to play that game, on average, they're all going to lose, right? On average, the casino's making $14 off you every time you play that game. Per person, they make $14 every time someone plays that game. Yes, you might have a winner here. This guy might win 1,000. Then they'll put up his picture. Oh, this guy won 1,000. You want to be like him? Come play this game, right? someone wins 10,000, they put up his picture, you know, like they put up the lotto pictures. Oh, there's a winner, you know, this guy with a huge check to kind of entice you to come and play. But at the end of the day, they are making money, right? So it's like a game of random chance, but it's not random because the probability tells them, in the long run, that's what we're going to do. You can come up with a business that runs on chance, like an insurance company does, and you can reliably and predictably make money. And we know it works because it literally it works. We have these companies, we see their earnings, we know how things are going. And as long as all the employees behave, they will have pretty much predictable income levels. So this actually works. It's interesting. A lot more I could say there, but let's go talk about the honey badgers. Do you guys really not know what the honey badgers are? Never heard of it.
There's a YouTube video about
They fight snakes.
You watch it?
Like my other class liked to know about it. It was like this meme that was going on for a while. Okay, never mind. It's Psalm 15. The honey badger just crazy. I'm hearing it in the voice. I was in that video. Okay, the most fearless animal in the animal kingdom. Overall, there is an 84% chance that the honey badger don't care. Okay, just take sort of one. It's from the script. Assume honey badgers are independently non-caring, and suppose you manage to gather 55 honey badgers because you're that crazy. What is the probability that all the honey badgers don't care? How did you actually solve this?
We did only 4 to
So this is the probability. So you have 55 of them. What is the probability that all of them don't care? Well, that means the first don't care. And the second don't. And pretty much it goes all the way to the 55th. And how did you do it? Well, the probability, because it's independent, you can actually multiply all these probabilities. Because they're independent, and they're all actually 0.84. So this is 0.84 to the 55, which is roughly what? 0.008%?
Yeah.
So it's not likely that they're all not going to care. Okay. B.
The presence equation, so 55 choose 4.
What equation?
Binomial.
Why would you put it into a binomial?
Because there's two choices. Either he cares or he doesn't.
Okay. Yeah?
They're all independent.
They're all independent. Two outcomes, all independent, and what?
Trying to find probability that it's after 42. Don't care.
Yo, that's not what makes binomial, right? There are three things that you should.
Oh, it's the same chance. Like they each have. It's 0.84 for each. Probability didn't change.
So it was two outcomes. They're all independent, and the third thing was you're repeating an experiment. You're doing the same thing over and over, right? You ask one hundred, do you care? Do you care? Do you care? Do you care? Come on, tell me you care, right? You're asking them if they care over and over. You're repeating the experiment. There are only two options. It's either yes or no, and they're all independent. That's what makes it binomial. So you need to know that you can do that because it's possible that a binomial would not work here. So it's binomial because of the three conditions fulfilled. Which were mentioned last week. So here I'm going to let x be the number that care, don't care. We're counting success that they don't care. And so this is, and here n equals 55. P equals 0.84. Q equals the complement of that, which is 0.16. And in part B, they're asking for the probability that x is equal to 42. What's the probability that it's exactly 42? Well, now we put it into the binomial formula. That is 55 choose 42 times 0.86 to the 42 times 0.16 to the what? 13. It's just that guy and then 55 minus that guy. And that was 4.32%. More likely that exactly 42 of them will carry than literally none of them will carry. And part C. Probably that between 28 and 30 would care, don't care. What is that asking? It's asking that x is between this, which we know for binomial, it's going to be the sum of them because you have they're mutually exclusive. So this would be just 55 choose 28.84 to the 28.16 plus 55 minus 28. Times 0.16 to the 26 plus 55 choose 30, 0.84 to the 30, 0.16 to the 25. And this was? 0.0000264. Okay. Not very likely that between 28 and 30 are more care. On average, how many do you expect to care? In other words, for D, what you're being asked is the expected value of x.
46.2.
How did you get that?
You take the number of trials, which in this case is 55, and the probability of success, which is 0.84,
Okay.
and you multiply them together.
Yeah. So technically, what we would do is take the probability of one of them not carrying times that, plus two of them not carrying times that, plus da da da, plus 55 of them not carrying times the probability that 55 of them not carrying. But it turns out that this will actually go down to n times p. Now, that's not in general, this is for a binomial. I.e., did anyone actually do this?
No.
So in my other class, someone used the TI-89 and had told it to add up 55 of them. And it's like, well, that's what we thought the answer would have been in the first place for a binomial. You're doing something n times, the chances of it happening are p, so it's just the percentage of these number of trials will be what I would expect to happen. That's something that you can know in general. So that's actually a general fact. It applies to the binomial. It doesn't apply in general. The standard deviation, by the way, is the square root of NPQ. You don't need to know that, that's for like statistics. But you can prove this, I'm not going to prove it because I have to talk about summations and stuff, so we're just going to move on. It's n times 2. So in this case, it's going to be, we had 55, and there's an 84% chance of that happening, so 42.6, you said?
46.2.
46.2. So roughly 46 of them won't care. It's the expected value. Okay. And now the hard one, which wasn't so hard because I picked an easy blood type. A minus would have been a little harder, but I typed A positive. I thought I typed A negative. Okay, this is problem 16. How did we do problem 16? What did we do? So, let's read it. You have 4 kinds of blood types, O, A, B, and AB. They occur in population with these frequencies, 0.43, 0.41, 0.11, 0.05. That's the percentage of people who have these blood types, roughly speaking. There's also a blood protein factor called the RH factor. It can be positive or negative. Chance that you're positive is 0.86, chance that you're negative is 0.14. And we have a chart that tells you each blood type, who they can donate blood to, who they can receive blood from. Now, A. What is the probability that a random person can donate blood to a person that has A positive? Yeah.
Well, you add up the probabilities of A positive, A negative, A positive, and O negative. So pretty much you just disregard the RH plus and RH minus probabilities and you just add the
Right, this means they're A positive, or they're A negative, or they're O positive, or they're O negative, which basically means they're either A or they're O, right?
which gives you 84, because you're adding 43 and 41.
Right, because they're mutually exclusive. One person can have different, 2 different blood types. So this is probably of being A plus the probability of being O. Mutually exclusive. Some of the others would have also required you to use independence, right? Type plus instead of minus. Okay, so this is going to be A is 0.41 and O is 0.43. So there is an 84% chance that if you pick a random person off the street, there's an 84% chance that they can actually donate blood to a person with type A positive blood. Okay, part B. How do we do that? So suppose the hospital needs 5 units of blood, right? So someone comes in, they were in an accident or whatever, and they actually need some blood. They need 5 units. 8 people go into the donation center. Each person can only give 1 unit of blood. What is the probability that at least 1 unit of blood can be found for the patient?
We did 1 minus probability of none.
So probability, so let's call this something. X equals number of people who can donate. Then in part B, part 1, it asks, what is the probability that X is at least 1? At least 1 person can donate, which basically means 1 or 2 or 3 or 4, all the way up to 8. Or, that's the opposite, 1 minus the probability of X is less than 1, which pretty much means 1 minus the probability that X is 0. No one can donate. What is the probability that no one can donate?
Let's do the formula with 0. Okay.
What formula?
The n choose k, d to the k,
How do we know that applies?
because it meets all the three conditions.
What are the three conditions?
Hold on.
Huh?
It's being repeated. There are only two outcomes, and each outcome is independent.
So in this situation, note, you didn't need it here for this part. It'll be needed for the others. Note, x is binomial. We call it a binomial random variable. I'll talk about random variables tomorrow, as well as Markov chains. I'm very excited. Is binomial because you're repeating an experiment. You're testing 8 people to see, can you donate to this person? Yes or no. There are only 2 outcomes. Yes or no. This person can donate or they can't. And they're all independent. You have 8 random people walk into a blood bank. We don't know they're related. We don't know anything. They're independent. One person's blood type has nothing to do with the other. So it is binomial, which means I can think of this as 8 choose 0. The probability that they can donate the 0 times the probability that they can't donate to the 8. You'll notice that these are all 1s. And so that's just actually 1 minus 0.16 to the 8, which makes sense, right? Means the first can't donate, and the second, and the third, and the fourth. They're all independent. You just multiply them. So you multiply 0.16 by itself 8 times. That's probably that no one can do it, which means probably that someone can do it. I think that's going to be a pretty high chance. It's
0.99.
It's like 99.99. We're sure that at least one person can donate blood to this guy. So if you're A positive, you're in luck if you ever need a blood transfusion. I looked at this table a really long time ago. I don't remember how reputable the source is, but these numbers are probably actually true. Two. Probably that the hospital will obtain all the blood it needs. What did you do here?
Well, it was at least 5, so we
At
did,
least 5, right? So x is going to be greater than or equal to 5.
So we did 1 minus the probability of 4.
Okay. Is that easier?
Yeah. Well, I thought it was.
Yeah, that's harder.
We did something different.
What did you try?
We did doing the same theorem, adding the chance of having 5, 6, 7, 8.
Yeah, which I don't think this is easier, because you could directly just add them, right? Or so you could do the probability that x equals 5, 6, 7, or 8. Which means you're going to have to do the formula 1, 2, 3, 4 times, which yes is a little bit annoying. But then if you do the opposite, what would you have to do? Well, the opposite of that is 0, 1, 2, 3, 4. 1, 2, 3, 4, 5. You have to do the formula 5 times by doing this switch. I'd probably do it directly. That seems easier to me. So they'll both give you the same answer, but this one is less annoying to actually complete. So it would be 8 choose 5, 0.84 to the 5.16. 3 plus 8 choose 6, 0.84 to the 6.16 to the 2 plus 8 choose 7, 0.84 to the 7.16 1 and 8 choose 8, 0.84 8.16 0. And finally,
It's about
97.
97.3%.
0.3 something. Hospital will obtain exactly how much blood it needs. What is that asking?
You just do the same theorem for 5.
Yeah, just do 5. So in part 3, just do the probability that x is 5. They'll get exactly 5 units, exactly what they need. So that's just going to be just one of these. That's going to be this guy. 8 choose 5, 0.84 to the 5, 0.163. What's that?
Uh, 9.5, 2 weeks.
They're more likely to get more than enough than to get exactly enough. So we'll stop there. Start mark off these tomorrow. Okay, I'll check. I remember seeing your email saying that.
Yeah.
So, yeah.
Okay, thank you.